visible light it seems to have no color to us. But if I put that through a prism, I can actually obstruct the path for the different colors that make up light, because they each have different wavelengths, as we discussed. And so I can make some slower than others artificially, and I can see what colors actually make up visible light. And obviously, some materials interact optically differently from others, and so you could see some materials as red, some materials as gray, some materials as pink, and so on and so forth. Okay, and that is a continuous spectrum. Light has a continuous spectrum, but certain objects have specific colors, so it'll be just here, or just here, or just here. Okay, what chemists have noticed, though, is that when they had gases of particular elements, so in this particular instance is hydrogen, and they put that through a prism, so it looked a little pinkish or something, they put that through a prism, they noticed that they don't get this continuous spectrum. They get this line spectrum here. So hydrogen happens to only show these four colors. Okay, right here. So two of them are in a blue purple thing, and one of them is a light blue, and one of them is red orangey type thing. Okay, and don't worry about this equation, but this equation basically by Rydberg predicted basically what these four are. He just kind of like fitted it and thought it would be a general rule. It isn't. So don't worry too much about it. But basically, they tried to model it. So you can see people started thinking about how do I model what this stuff looks like inside the atom. And so this is called a line spectrum. And that's why I got that lithium example a few minutes ago. We talked about the red light in lithium. It's basically this kind of stuff. You would put lithium gas in this, and you would put this through a prism, and you'd get whatever light lithium has, and one of them is red. Every element has its own line spectrum. So the line spectra are used as sort of fingerprints for different elements, and chemists certainly use this when they have unknown compounds and they want to identify them. If they put them through something that can measure the colors, the absorption of colors, they can try to determine what this stuff is made out of. So let's look at an example. Well, actually, we'll look at an example in a few minutes. I want to move and shift to the Bohr model of the atom, of the hydrogen atom. All right. So classically, Rutherford's model is what you probably have in your mind. If I asked you what's inside of an atom, you'd say, oh, I have a bunch of protons in the middle, and I have these sort of like an interplanetary planetary orbital type thing for the electrons. Some electrons would orbit the proton in this particular way, and they have an orbit around it. Okay, that's nice and all, but this predicts that there will be some sort of a collapse eventually, as the electrons would lose energy and collapse into the protons, which thankfully doesn't happen. So Bohr proposed that, as a matter of fact, this is not true. Electrons can't just spin wherever they want like that, and they have to have allowed energy states, and that's why they don't lose energy. They can't have less energy than in that state or more energy than that state. If they do, they have to kind of like jump like a quantum type thing, a quantum leap from one orbit to the next to get to the next level. Or if they're trying to go back, they would emit this energy as light to go down to a lower level. Okay. So as I am if I'm absorbing energy, if we go from one orbit to another, I will need energy to be shined onto the material. If I'm going back, I'm going to emit energy. What do I mean by all this? So basically what he proposed is he said I have the nucleus somewhere in the middle, okay, and I have allowed states. So it is sort of like planetary, but so let's have these states, okay? An electron can exist here, or here, or here, but it cannot exist in the white, only on the black paths. And if I want an electron to go from this orbital to this, I have to give it energy. If I don't give it enough energy, it won't do it. It's like the quantum thing we just mentioned. I have to give it enough energy for it to jump here. And same thing here. Or I can go from here to here if I wanted to, if I give it enough energy. But I have to give it this particular amount of energy to be able to go up and down. If an electron goes from a higher energy level to a lower energy level, it will emit energy, and that is usually going to be visible light. So we will actually be able to see how much energy is going to be emitted by an atom, by an electron, when it shifts from one orbital to the next. Okay, and he predicted this equation to explain how this would work. The energy between two orbitals is going to be equal to this constant in joules times the final orbital minus the initial orbital. Okay, and this is going to be in joules again, and it's going to be delta E, or it's equal to h nu, which is equal to hc over lambda, which we've done already, so you could see where this comes from. And I think now we're going to do an example with Bohr's model, and that will, I hope, make more sense. I should note that Bohr's wrong. Bohr was not right, but it was a deviation from what was thought to be correct for quite a while. And let's do an example that explains how this works. So an electron releases light with a wavelength of 103 nanometers. Okay, as it travels from to the first energy level of a hydrogen atom. Okay, so by the way, if you want to know what kind of equation to apply when these models, if you see hydrogen atom is going to be the Bohr model. What was the original energy level? So what am I asking you to do here? So if you look at that picture I had before, if I have the nucleus somewhere in the middle and I have these orbits around, I want to know, I noticed, he noticed that as stuff traveled to the first energy level, which is the closest one to the nucleus, some light was emitted. Light got emitted. He observed it with his eyes, and he measured its wavelength as 103 nanometers. That's what he saw. And then he wanted to know, based on this, what was the original orbital? Was it number 2, 3, 4, 5? Was it whatever it was? He wanted to know. So what we'll do is we'll go back to this equation that was proposed here, and basically we're looking for the initial n. We know that the final n is number 1. We want to know what this one was. It was 2, 3, 4, 5, 6, whatever. And we know this is given to us. It's always true, negative 2.18 times 10 to the minus 18 joules. And this is going to be equal to this. So we get to choose what we want to make it equal to, whatever we have. So I gave you the wavelength. I remind you, this is a constant. This is a constant. So we don't have to be given that. It's a constant. And this I gave you. So this makes sense. If I look at this particular equation here, you have H, we have C. We don't have this. We're looking for this. We have this. Sorry, we're not looking for this. We have this. We have H, we have C, we have lambda. We have this. We know the final. We don't know the initial. So this makes sense. It will be one equation, one unknown. Okay. You don't have the frequency, so don't bother with that. And you don't have the energy, so don't bother with that. So go here. So I'm going to use that equation here. HC is going to be equal to negative HC over lambda. Sorry, is going to be negative 2.18 times 10 to the minus 18th joules times 1 over n final squared minus 1 over n initial squared. Okay, so let's put everything that we already know. We know H. H is 6.626 times 10 to the minus 34th joule second. Great. We know C is 3.0 times 10 to the 8th meters per second. Great. We know lambda, but lambda is in nanometers. Very not convenient. So I'm going to just convert this to meters. So I'm going to skip this because I've already done it several times in the other examples. This is going to be 1.03 times 10 to the minus 7th meters. If you don't remember how to do that, go look at the other examples from this chapter or review your dimensional analysis. So this is going to be equal to this, to negative 2.18 times 10 to the minus 18th joules. Okay, and times, this is the stuff I have some of it, not all of it. I know that the final is 1. I don't know the initial. So I'm going to solve for this, n, okay? So if you multiply this is going to be a number, some sort of a number. So it'll be number is equal, number 1 is equal to, this is another number 2, is 1 minus 1 over n squared. So basically you just have to solve for n. So you divide this, you bring this to the other side, whatever that number is, and you get this. See that? And then I can swap locations for this, right? So if I swap locations for these two, I get this. And then what I do is I get this, and once I get this, this is another number. Let's call it number 3 is equal to that. And then if I want 1 over n, and I want n, it will just be, n will be, n squared will be 1 over this number 3 thing. And then I can find n as the square root of 1 over this number 3. Okay, so I could do that. So you can go on, and this is just playing around on the calculator, or just trying to solve this. Okay, so I trust that you can do this algebra. If you have problems with it, let me know. That was a very sketchy way of doing that to show you kind of what to do with this without actually showing you the numbers. This is kind of like the machinations behind that. If you do that, you get that 1 over n squared is 0.88888 forever. Okay, which is 8/9. Okay, so then you solve for n, so it'll be 1 minus this thing, and then n should be 3. So your initial orbital was number 3. Okay, so this is how you do this stuff for the hydrogen atom. As I mentioned, whenever you're seeing questions asking you about orbitals in the hydrogen atoms and energy levels and things like that, think of the Bohr's model, and you'll be fine.